Next, I'd like to welcome Professor Ping Yi from the University of Akron.
Good. Hello, still good morning. Thank you for coming. You may have noticed that the title listed here is different from what's showing on the program there. That's a mistake when we report the presentation title. However, okay, the main thrust of the contents, still related to control strategy and the algorithm and everything. So this will hopefully serve for the same purpose. And now the topic is junction of offset intersections. How do you centralize the control? Now, if you know traffic operation and signal control, the offset intersections, especially when many of them are together. What you see here is just, or just two T intersections, but we have 4 or 5 together, and it's always a problem for traffic engineers to do a efficient control with the signals. Okay, now we'll get to that part later. But unfortunately, this kind of odd geometric design exists in every city, especially older part of the cities, and where you have a lot of activities and traffic and everything. That's why in this research, it's a small-scale research. Our objective is to study the feasibility when we have autonomous vehicles. Okay, and how do we handle the traffic problems and hopefully improve not only the efficiency but also the safety. All right, let's get to the details. Now again. On offset intersections, we all understand, but when you have several of them with the different OD patterns, especially when the OD patterns are involving some turning movements rather than just going through, okay, and then I really can have a really big challenge for signal engineers, and it will require probably multiple controllers and how to coordinate. But once there's anything going on, the OD pattern changes. It's always a struggle to go through, and a delay and accidents and everything. In addition to the environmental impact listed here, and so the thinking is we have autonomous vehicles where we have communications between vehicles and the infrastructure. We may be able to have the traffic flows guided through, and then even without using the signals. So that is the thinking. Now, getting into a little more on the problems. Most cases, okay, I can say most cases, we have a problem with a capacity, these kind of locations. And especially if you're involving a lot of turnings, okay, we'll see, we have another picture to show you that. When you are waiting in the middle block, making a left turn, cutting through the opposing traffic, and there's always a challenge there. Now, that's on the operation, but for the safety part, a gap acceptance. If you're using stop sign control, definitely there's the efficiency problem. But if you signalize all the intersections, I would say 4 or 5, the T intersections, and they're all offset, it's hard to do the coordination. And even for gap acceptance for vehicles coming out, making turns, and you have to have a signal to protect. Otherwise, you could have problems. And so collisions in this area is reported increased by 35%. And rear ends because stop, go and stop suddenly, and rear end, and also the right angle accidents. And when you have a larger vehicles, the sight distance is, it's poor, okay, it's blocked. So those are the problems, and we're thinking that if we use autonomous vehicles, maybe we can have a guided, traffic flow, then we can avoid all those problems. So the methodology is we can use the communication capabilities and to receive the OD information, the platoon size, like length, and also what's the approaching speed. And then we can do, before even they join the system or a junction, we call it, intersections, we can adjust the speeds. So give them, assign a certain speed for them to go, that will avoid the conflicts. And possibly, through those conflict points, CP means conflict points, by a safety gap set so that we can avoid the conflict, and then nicely, possibly, we do not have to use a signal, control, and then they just follow the instructions go through. So mainly that is the whole guideline. Again, this is a small research effort, but we're trying to develop methodology for that so that if it's feasible and that'll be good feedback. Anyway, this is one example here. You can see that we have, let me see the pointer. It's hard to see, it's very small, tiny, not like mine. I have a very big green spot, but you can see we have vehicles coming. This is the main road, quote main road, and they have a two-way traffic, and we have some coming and one way. But if the side streets are also both way, two ways, and then they'll make the pattern really, really complicated. And that's where the problems, like I go through these kind of intersections, not on a daily basis, but often, and different cities. I live in different cities. It's always a problem area to go through them. To explain more about that chart there, you can see that we have vehicles coming in from A, B, D, and E, those are approaches, and we have a total of 14 OD pairs. Just want you to come back. Let me see. Yeah, you can see that vehicles can come from the direction and can go out from here, can go out from here and here. So, but then if you come in from a side, you can go out there, go out here, go out here, go out here. So you can have a multiple. So total, you have like a 14 OD pairs, and especially involved in turnings, when you have a lot of traffic there, can really create problems. So the last line in this chart, in this slide says that at least every traffic, a platoon coming into the system will go through at least one conflict points, and at most can go through 4 conflict points. So that's why where the complication is. That's why we have a lot of traffic operation and then safety problems. Now this one shows the simple methodology interference matrix. Just say that, for example, if you're coming from A, the platoon, oops, how do you go? Oh, let's go this way. If you go platoon coming from A going out B, then definitely you go through this conflict point 1. But if you're coming from A to going to F, then you have a 1 and a conflict point 3 and conflict point 4 and also conflict point 6. So you have 4 conflict points. So this is just, we have so many, pairs coming in. I'll just show you an example. That's what the interference matrix means. And so started to do the modeling, we need to first decide the platoon length. You will not only have the number of vehicles, but also the inter-vehicle spacing you have to consider, and that's S, and number of vehicles, and all those things. We can just consider the whole platoon as a whole body, and then not any part of that will not be in a conflict with other platoons. All right, so this is another one, just a simple one shown that if you're coming from A, this is the distance. Oh, keep doing that. This just shows that if you come from A, you go to conflict 1, 2, 3, 4, and you can see this is the the distance that you have to go depending on where you're going. You can see that this is mainly the distance that cover not only the actual length you have to cover from one intersection to another, but also you have to cover the approaching distance. Okay, when you're coming in, before you join, the system will know you because through the communication, report to the system how many vehicles are there, so the platoon length. but also how fast they're going, everything, and all this information will be taken into in the account. In this, this is just showing one coming from A, and then you have multiple. So we're just using this for concept introduction. And this table shows the potential platoon conflicts. Like, for example, you're coming from A, and then at conflict point 1, you have potential conflict with those platoons. And at the 3, you could have this. That's you're coming from A. That's why you always start with A. Okay, you could have a conflict with coming from B, from C, E, and so on. And if you're D, then this is where you possibly have a conflict. So those are, this information is very important when you try to develop the solution strategies, so you know where to look at as the system base. Methodology is, just very simple, that we try to avoid, conflict. If you have 2 platoons coming to a conflict point K, for example here, then depending on where you're coming, where you're going to, and also in another platoon where you're coming from M going to M to N, want to make sure and they are separated. Doesn't matter which one coming in first, so we have the absolute sign there. They will have to be greater than a preset gap, so that to enhance safety. And the whole objective, of course, is to, by changing the speed of the platoons coming in, and then with the distance of travel there, we want to make sure that the time arrival for these different platoons coming to the conflict points are separated by enough gap, so that the whole thing, without stopping, may hopefully go through the whole thing even without the signal regulation. So that's the concept. Then how do you tell whether your solution is good or not? Then the whole objective is to minimize the total system-wide travel time in going through the entire junction. So again, the objective is to minimize total system travel time, okay? Or you want to say delay, but do a comparison, you will find that. So the decision is for you to see how much the platoon, the speed of each platoon should take, so that we can avoid going into the same conflict points with other platoons. And of course, in doing the work, you have to do the updates frequent, because certain vehicles or platoons when coming in, new coming in, but the old ones coming from the system will move out. So it's a continuum process. And then how do you validate whether your solution is good? Of course, on one hand, analytically, we try to get the system-wide travel time, and also and then we can verify in terms of the number of conflicts, because then we can record if you through the simulation. This project, again, we're still working on it. That's why we have only some preliminary results to report. You can see that this is generated platoons, and you can see this is the length, number of vehicles. This is in meters in length, and also the total length. And then the arrival, and we did not have anything on this column because in the random, you can assign the random, because you don't know which platoon come and where they're going to. So that's where we started to generate things, and this is the phi matrix or table, where you're going to different places. This is the distance, depending on where. It's not as certain. We have maybe there's too many digit points. Maybe we put probably for the distance part, because the meters, maybe we use 1 digit will be fine. But depending on how soon you are able to communicate with the system, report to the system, you are approaching distance. In other words, I'm coming from a side street or from a main line. Before I reach the system, I report to the system. So we do that also as a random fashion. And then not always at the same point, your platoon is picked up. Okay, so that's why you still have the different distances for the platoons coming from the same place. And then this is the first when you just use whatever speed in the platoons coming in, and do that, and then we found potentially this is at a conflict point 3. Okay, we could have a conflict. You can see that at certain locations. For example, you can see those two, 13.4, 14.6, They are separated only by 1.2 seconds, and then I think I have another shoot. Oh yeah. So you can see that potentially those two will have problems, although they have 1 point some seconds separation. For safety, we want them to be larger, right? I mean, depending on this is how you can determine. You want to make it really safe, 3 seconds or 2 seconds. But we, in this case, we set it 2 seconds. But obviously, you can see there's a problem with this. Okay, those two also. So then through, a modeling and so it's involves a nonlinear programming, it's a mathematical process, and we haven't done the simulation part yet, but this is only mathematical process. You can see that the system is able to optimize. You can see this is finally optimize the approaching speed for the different Platoons, taking this speed coming into the system. And then you can see that at the different conflict points, the times are all separated out, at least by 2 seconds. In other words, the same conflict point, you have this Platon, they're just separated by time, and we use 2 seconds. But this is good news because it means that mathematically we're able to solve the problem so that we do not have to, involve really signals. And then, but we understand some Platons will have to slow down a little bit, and some Platons, are lucky to get the same speed. So there is a trade-off, okay? But we will do, more work on the simulation part. We'll find out that, and of course, this is our next step. And finally, okay, I will just say that it's meaningful, this work. And again, this is a small effort. It's a small research effort. But we're we're very happy to see that this, at least the formulation is well posted. So what I mean mathematical well posted means you have a solution and feasible. I mean, it doesn't take, thousands of, or millions of dollars to get at it. So it's a very simple process. And, the results are promising, supporting, possibly in the future, you do not have in a signal-free environment, and possibly you can get this, worked out and efficient and avoid conflict and everything. So this is what a preliminary finding. And of course, we do more work, and especially through simulation, will confirm a lot of things we said there. Time is limited. I know everybody, needs to go on. Oh, actually, we have one more presentation. Any questions?
We have time for one question. Okay.
Thank you.
Sorry. Thanks.